you see already, of course, this is joint work with many, especially PhD students at our chair, but also beyond our chair. We have a lot of collaborations. So I mentioned here, hopefully the most important ones, but not all of them that contributed to our work. So a very short introduction, what we are doing. Our chair is active in the field of computational science and engineering. And therein we are, as Georg has already mentioned, focusing on the computer science part. And especially today, I will talk about what we do in the software design and also optimization area, and specifically code generation. So this is, of course, a very specific area that we are tackling. And that means I have to set kind of the ground. So first of all, our main work is the development of software frameworks. So that typically run on HPC clusters. So that's kind of the frame we are within. So we want to write software for large-scale systems. And more specifically, we concentrate on usually block-structured data accesses, block-structured grids, and deal with multiphysics applications. Main issues are here, of course, to get the best performance on a certain system. And this is also our main motivation for the code generation, as I will show you on the next slide. Because in principle, what do we use code generation for? We use it to get the search space complexity handled that is introduced usually by a lot of different choices that you have to take when you deal with multiphysics simulations. So besides the model, of course, the discretization, the solver, the platform, maybe an AI. So there's a lot of things that you have to choose. And from all of these variants, you then want to produce, of course, the best time to solution, or also maybe the minimal energy consumption code. So that means what is now code generation for us? It's basically the process of producing code that we can then use to execute on a certain platform. So how does this look in more detail? So if you look at this overview here of the process, then typically we start with an abstract, close to mathematical representation of our problem. So standard problem is here, for example, you want to solve a partial differential equation. And this mathematical representation we can write down in a very formal way. Usually, for example, you can describe it in a domain-specific language or using a simple Python abstraction, and then work with this maybe symbolically. From that, we transform this into a code representation that is also kind of abstract. So, of course, what does it mean to transform it into code? It means that we say each of the objects, the mathematical objects in the first representation, like U, is now assigned a certain data structure, for example. And then also, depending on this concrete data structure, we have to define operators on the data structure. So we have to handle data accesses. And these two things you need in order then to map it to a certain low-level code that is then, of course, at the end, architecture specific. And code generation basically means that we write those transforms that map from the higher abstraction to the lower abstraction level. Now,
yeah, sorry. Let's keep it interactive, okay?
Yeah.
So where's the boundary between a compiler that takes a sort of language and translates it into machine language right away and code generation? Because all you do is basically also you take a sort of language, maybe a DSL, maybe something higher abstraction levels, but still you translate one language into the other. So when do you call it a compiler and when do you call it code generation?
Very good, because this is exactly what I wanted to start here as a discussion. And you asked now about this part here, compiler. So a classical compiler is usually working on all programs. So you have a general language, like C++, Fortran. There you can formulate any kind of code. Can implement anything. It's a general purpose language. Typically, what we deal with is domain-specific things. So that means we restrict ourselves. So you cannot express everything, so to say, in our language or in the abstraction level. This, of course, limits what you can write down, but it also enables you, for example, to do optimizations that you cannot do in a general compiler because we can make assumptions that only we know. So very good example is, for example, when we look at HyTeG, there we know that we want to, for example, evaluate some quadrature rule or whatever, and then we can, for example, make a table of specific with specific entries where we say, okay, this we can pre-compute this part because we know we are dealing with this order, and then to keep it correct, so to say, the right convergence order, we can only evaluate it with this order, the quadrature, and so on. So very specific rules that you can only use if you know exactly what you are computing. And of course, a general compiler cannot assume that because it also has to compile other things, not only finite element expressions. Yeah, by the way, Daniel, who is implementing this, is sitting here. Okay, yes, but so this is just the start of the discussion, because I'm always asked, why are you doing code generation? Because code generation for us is really an approach, for example, to get portability to other platforms. And if you look at the diagram here, of course, so we are the developers, right? So for us, it's much more complex to implement such a domain-specific language or of course, the code generation pipeline compared to you write one manual code. Yeah. Also, this we have to be careful, because if you, for example, think about these, when you do loop blocking or so, and then you have some very complex code at the end, also may not want to do that manually, for example. So it's not 100% true, but in principle, I would say writing a code generator is, of course, more advanced and more difficult compared to writing manual code for a certain platform. Nevertheless, of course, you should get the best performance here. And we have the advantage, and this is, in my opinion, our selling point, of course. So we are framework developers. Of course, we also want to have users. Yeah. And after we have implemented our code generation framework, so for example, for lattice Boltzmann, this LBMPy, this can be used as a tool for a number, maybe also of other lattice Boltzmann solvers or frameworks. Yes, but that's just, as said, the start of the discussion. So this is code generation. Anybody knows why I have added the other things? So here the prerequisite is, of course, you want to write a software that runs on different platforms. So that's the basic assumption here. And what's your opinion? Compiler, standard PAR?
Tried it.
In fact, I know it from several industry partners. They follow that path because you just have C++ code. So of course, if you're able to express your C++ code using basically the standard library, then you can immediately, for example, port it to NVIDIA GPUs. Yeah. So it's how it works technically is basically you have a function call, I don't know, find or whatever, or sort, and the first argument is then the device you want to run. Yeah. For example, then it's parallel and it can be shipped to GPU. So that's a very easy way, but of course it is very general. So definitely very productive. You are quick if you have a C++ framework already, more or less out of the box, hopefully working if the compiler is working. But you get not the best performance. So of course, this scale here is not absolute, right? So it depends on the code. If this is now a factor of 2 or 5 or 10, this is very specific. So nobody has worked with standard PAR? Okay. So then maybe that's also new information now, interesting. So I would say if I would run a company and have a large C++ code that is very old and very expensive to refactor, maybe that's of course some way to go, theoretically. Just to run your code then on GPU. Okay, so that's the compiler thing. And all the other things, they require now more work on your side as a developer. If you have code annotations of pragmas, whatever, OpenMP, OpenACC, this is also very often used because it's also relatively simple for the developers of the frameworks. They just have in front of some loops, they put their pragmas and then hopefully it works. Yeah. In our projects, it's used in several big codes also, the OpenACC. So we are involved in several European projects where we have access to a number of codes, and those OpenACC, especially codes or accelerated codes, are found more often. Okay, but nevertheless, of course, you only can control this loop then, and hopefully it works then internally. The library approach, if you ask me, I would say this is the most, so most people would say they like Cocos and the library approach, I would say, currently. It may change. But of course, if you have this additional abstraction layer here implemented in a library, then you can just say, okay, I use Cocos. Based on Cocos, I have some data structure implemented, and then I just use this for my, I don't know, particle dynamics or whatever. Yeah. So we also discuss, right, for our project, maybe it's worth to play around with Cocos. I think the benefit of Cocos is if you manage to write your code such that it can, under the hood, use the Cocos infrastructure, then you get rid of all these issues, right? Because then you can always say, okay, Cocos will support that backend and they will hopefully optimize it for the machine, and then you are fine as a framework developer.
But aren't it two variants of library-based approaches? One is Cocos, which is quite low level as libraries go, because it allows you to write one code and then code meaning loops, for example. So primitives on the loop level.
Yeah.
But there's also a library approach, which has more high-level abstractions, like calculating, I don't know, a gradient or an integral, maybe a solver even, yeah? And this can also be connected to DSLs. So if you have a library that implements these primitives and you can map your high-level description, mathematical description, to some of these library calls, that's a very powerful code generation approach as well.
Yeah, I agree. So that, yeah, this is, as you say, you can also mention BLAS, maybe even, right?
I think that's like Cocos.
Yeah, yeah.
Sort of the same level.
Yeah, yeah, but BLAS even, yeah, maybe yes, but the yeah. Okay, now you can discuss on which exact level is that. But yes, for example, if you have, I don't know, PETSI or something like this, so standard solver thing, or Ginkgo, yeah, those libraries. Yes, true, but yeah, I don't consider them to be kind of a new approach here, but kind of they have influences of several things. So for example, Ginkgo itself is a framework that uses under the hood such a version, and they have several implementations of kernels for different backends. So they also kind of make use of these things. Yes. Any remarks from your side or anything you want to add? So maybe you see the right corner there. I added that today because yesterday I gave a talk in Munich, and the first question was, why don't you use AI for programming? So I give this question to you. So why do you program? So why don't you use AI for programming? Of course, kind of a...
Because it is more work to fix. I had it wrong than just doing it yourself.
Yeah. So yes, of course, we are also playing around with these AI things, Claude and Co and whatever. Currently, I think they are not in a stage where you can use them in the productive software development on that level, but maybe in future. So definitely they are useful tools. So I use it, of course, in my Visual Studio Code, and of course they write my job scripts and things like that. Yeah. So kind of routine tasks they can definitely do. But I don't want them to write my framework code, to be honest. So not so far. Yeah. So maybe in future,
you really want them to write your job scripts as well, because a lot of things can go wrong in a job script. You check anyway. A job script is, of course, it's just 20 lines of code, maybe, or 100, but it's more complicated here. But you still have to check.
So I'm kind of old school and don't use the agentic AI and just let them run. Then I check it manually before it runs. But but this is the next step, of course, right? So just let it run the agent and then see what happens, and then I get a angry call from yeah, okay.
Incidentally, there's an HPC cafe in like 1.5 hours that has this as a topic.
Oh. Yes. Yeah, so I guess so. I saw it for maybe if you're talking about it, I saw it for some students really sitting down, working at the cluster, having the Claude CLI, and that really was very smoothly, right? So yes, if you know what you are doing and what the AI can do correctly, it's fine. But so I in order to conclude that, I think otherwise we would never get to the second part. If you ask me personally, I think in future there will be compilers that are maybe internally using AI, maybe automatic proof things, whatever. Yeah. I don't think there will be a ChatGPT that writes my HPC framework. So this is maybe I'm wrong, but So currently the technology is more like an assistant, not completely autonomous. Okay, and now let's really jump into the real topic. And that's basically how we use code generation within our frameworks. And I have announced I want to present two examples, waLBerla and HyTeG. Then I remembered that the way to those developments was basically via another code generation framework that I want to briefly mention that was earlier, just to motivate why we started to work on that. So in principle, the first code generation tool framework that we have implemented was ExaStencils. So that was quite some time ago, maybe 10 years ago. So the end of ExaStencils was around 2020. And why do I mention that? Because this is a very specific kind of code generation, and that's whole program code generation. So that means that's more or less a full compiler. Again, your question, what is a compiler? So that was our first where we played around with code generation. So we had there an own language, domain-specific language. So basically text, even in different layers of abstractions. And you have this text. This text you basically parse. Then you have an abstract syntax tree. Then you do code transforms and you spit out at the end, for example, C++ code. So that's more or less a full compiler where you can do all of fancy things. The only difference, the main difference to a real compiler is that our backend was always C++, so a higher level language, so not like assembly. Okay, but that was the start, and we were able to implement their efficient multigrid solvers. After that, we also extended it in a sense, and this is now important to mention, that we now could support a different kind of discretization and grids. So that means our domain-specific language was very specific to structured grids and multigrid solvers. So this is really the difference to a real general purpose compiler. It's only limited, the ExaStencils, mainly to generating multigrid codes on structured grids. And then we extended it, and this extension, and that's why I mentioned it, took again several years. So that means this is the drawback of these code generation things. The development is really time consuming and takes usually in the range of a PhD thesis to have really a substantial improvement on such a code generator. And because of that, by the way, here I show you some example that to get an impression what we do there internally. So in this version, we had basically also from Python. So we started from Python. We had then transformed these element integrals into something like this that could then be mapped to code. So this we did internally. And this is, of course, similar in spirit to what we also do in HyTeG, for example, to evaluate those things. Good, and then, yes, we run these things. And I want to show you one example use case, what you can now do. So if you have such a code generator, you can now, for example, say, okay, I have some model, higher order, and I can split now the order and run some parts on one hardware, so on one architecture, and another part on another architecture. And this comes more or less for free because you have your code generation pipeline and you can just say, okay, this code executed on GPU, this code executed on CPU. So this is now kind of what I had on my slide for the user as a benefit. Once you have spent the years and the effort in implementing the code generation part, then those things are possible and more or less simple to do. Yeah.
Speaking about the user's perspective, how do they interact with these sort of code generation pipelines? For them, is it just a Python script that does the code generation, compilation, and running of their situation formula for them? So is it just one Python line and a Python script? Or how do they interact with this?
So the typical user stays in Python. Yeah. Because that's the idea. So because if you want to dig into the details, so for example, I can come back then when I talk about the HyTeG operator generator. So there you have Python, and then you generate, for example, a C++ class, including some things, functions and so on. Of course, as a user, you don't want to touch that. Maybe you want just to generate your things and then run. So theoretically, you don't need C++, but I can ask the developer, is this true?
Yeah, more or less. So the way we do it on the HyTeG code generator, we have one concern is that some of the transformations, or mainly because the SymPy stuff, is time consuming, more time consuming probably as possible. And so we wanted to shift the generation mostly to an offline phase, and also that not everything is generated every time you compile your code. And so what we have is basically one Python script, and it reads some configuration files, which are like, we chose to use TOML. And there you just specify, okay, I want to have a finite element operator that solves or that implements this particular bilinear form using this particular element type and this polynomial degree and so on. And then this is run in a CI pipeline. It just has to be present in the repository as a config file. And then the CI will generate the code, and then is added as a submodule into the main finite element framework HyTeG. Then it just can be included there like any standard header file. It will be built together with the rest of the framework.
So I look in your face. So I think, and I think this is good that you explained it like that. The pipeline becomes more complex.
Mm-hmm.
So it's not like you have only one programming language, right? Or only C++. You have your GCC and that's it. Of course, if you involve Python, C++ things, then you need a more complex pipeline, but this can be automized. So,
and it's not necessarily the most easy setup, but I know from the waLBerla is set up a little differently because the code that they generate is much smaller. And so they are basically, I think, so I'm also not completely involved in that, but I think they have, together with their C++ code, they check in small Python scripts. Then you just add one more line to your CMake file, and then the rest happens automatically.
Yes, I come to that, but basically because you mentioned it now, I can also say it now. So what you are doing is kind of operator generation, right? So finite element operator. Here I'm talking about whole programs, so that includes not only the kernels, also the communication, MPI, and also the data structures. So this is very complex. So you also generate here the data structures. And in waLBerla, we usually do kernel generation. So you have specific kernels, for example, for the Lattice-Boltzmann method. You have a specific kernel maybe for a boundary condition, or you have a specific kernel for packing, unpacking of communication things for MPI. And this, of course, is then kind of more or less invasive to your framework. Yeah. Right. Maybe I just quickly say a few words. So Here we also did some evaluation of the performance. So that was basically done by Sada, one of our former PhD students who has developed the Goddess framework. And now I come back a little bit to what I just said, this coupling, because in fact it's not trivial. So you have explained it, therefore we're perfect, yeah. So if you want to couple generated code and handwritten code, you really have to be careful, right? So and to do it efficiently, because of course you can generate a library and then just link it together or whatever. But what we want to do, we want to have really a very tight coupling typically. So we generate basically code then for HyTeG, that you can use when you run it on a supercomputer. And therefore, we also had to think about these coupling libraries together. And we came up, and now I have again some figure that highlights one of our workflows. I want to highlight it here because it contains both exostencils and waLBerla. So this was implemented by Richard. So he basically coupled both frameworks together. And what is interesting here is that the upper part is, of course, the code generation, where you have also the parameters like what you want to solve here in the knowledge file or on which platform you want to solve it. So all of this information, of course, has to be known to the code generator to be able to generate efficient code. Then you use your internal compiler, generate your basically files that contain C++. And out of that, we now create such a library. And this we link together with our waLBerla. So that's how we have done it here for this use case. And of course, in this way, we can now basically use waLBerla coupled to a multigrid solver from exostencils. Yeah. And this was here kind of a result, a scaling result on SuperMOOC, where I also mainly want to show you here our DSL. So this is kind of a more abstract, higher level representation where you find here. So this was done with a finite volume discretization, for example, and here you find, for example, the integrals over the faces. So this is how the domain-specific code looks like then that is generated from the equation. Yes. Last slide about that, because this was a relatively recent result also in LRZ, where we were now able, because as I will tell you later, waLBerla is not working on structured grid, it's working on an octree-based data structure. And of course, we also wanted to support multi-grid on these grids or that data structure. And this is basically first prototype that also supports the generation of multi-grid solvers on waLBerla's octree. Good. Questions so far?
What about the actual performance of the generated code?
I have more results on that, but I can say in general, you are faster. Also because it's quite tedious, for example, to insert sizes, for example. And of course, if you generate code, then all the domain sizes are known, loop sizes are known. So of course, that makes it easier for the later on compiler. So usually we are most often faster than the standard code, but at least as fast. But we will see some in-depth results now, starting from HyTeG, in fact. So there is a new paper now from 2027 that was published, very highly ranked in the Science journal. And here, basically, Fabian and Daniel have shown some results in HyTeG. Again, what is HyTeG? Just to motivate that, this is a software framework that was originally developed at the LSS, our chair, starting around, I would say, even 2000 or so. So Ben Bergen was the first one, I think, that started to work on that, had a PhD in that direction. And afterwards, a number of other PhD students, and now together with the TUM and LMU, we have used it lately for earth mantle circulation. And the specific thing is here that we use this kind of grids here, where we start with a unstructured grid of tetrahedra. And this we can then regularly refine. And by this regular refinement, if you do that several levels, then you have, of course, regular access patterns, and you can write efficient multigrid solvers for that. By the way, this is also not quite true, the CPU clusters. I think currently we are working on also GPU prototypes, right? So that will be maybe the next year or so. Yeah. Okay. Yeah. How about time?
20 minutes.
I think I skip a few slides. So this is just again the problem setup. So basically, as mentioned, it's a finite element code, and especially I want to mention that it works matrix free. So we do not store the matrix. It works on these kind of special hierarchical hybrid grids, and it uses code generation. And the question is, of course, why do you want to use code generation here? Because again, we have a lot of different parameters. So first of all, we have different weak forms, so different PDEs that we want to solve and optimize for. We have maybe different precisions, half, single, double. We have different architectures. Maybe even if you focus on CPU, there may be different kind of SIMD, depending on the architecture. We have different discretization spaces, so the Laplacians, or the vector ones like the Nedelec, and others. And we want to apply a number of optimizations to the code that are relatively tedious to implement manually, correct? So this was here one of the main, of course, reasons not to have to implement all of that manually in all of the variants. So basically, it boils down to such a element loop. As we have already mentioned, we do here operator generation. So basically, the operator is fully generated as a C++ class. And that means, this is the overview here, that you define some parameters, like what do you want to solve, so the weak form, in which function space, on which architecture, for example, which quadrature rule you want to apply, and on which precision you want to run. And then the code generation starts. You insert that in Python, as we have heard, and the output is then a C++ code. Yes, and now I mention one or two optimizations that were done here. So the first one is the basically the loops. So the order of the loops, how we run through the three-dimensional tetrahedra. So here, originally we had a way where we have 6 different parts, so to say, where we have split it in 6 loops and then performed a sweep over all of them. And then we were done. This was because they were consecutive in memory. And we fused that now using code generation into basically the right variant to do it not in this way, directly working on the tetrahedra, but working on cubes. So therefore, we were able to reduce the amount of memory that has to be transferred, because if you do it like that, then at the corners or at the interfaces, you have to load some of the data more than once.
There's a tipping point with loop fusion. If you fuse too much, of course you save data traffic, but if you fuse too much, the kernel might become too fat, and then there's register spills. The compiler doesn't really know what to do with dependencies and registers and stuff. So is there any control in the code generation where you could say, okay, if the kernel is longer than X lines of code or has more than X variables, please stop and leave it split? Is that possible?
I think it's not automatically done, is it?
So right now it's not decided automatically which variant we choose. So we have to specify that as an input parameter. But what you say is certainly true. I mean, we have observed this for some kernels. The sawtooth loop is faster than the cubes loop, simply because on these tetrahedral finite elements, you can't do some of the traditional flop optimizations that you have on Cartesian elements. And so some of our kernels are not memory bound, but compute bound. And then doing one element at a time is faster than doing all of them at the same point. What is of course interesting is these kernels which are somewhere in between, where you don't get optimal performance for either of these cases. And of course you could, and we would like to try this, do something in between where you split it in not into 6 loops over the grid, but over 3 loops or 2 loops over the grid, then handle 2 or 3 elements at a time. Yeah, and of course automating that would be also very interesting.
Or having some kind of performance model in the loop that gives you a hint.
Yes, so of course we did some alongside performance modeling, but not automatically. So it's not included, right? So it's manually done. I think because of time, I have to jump now a little bit. Here is, by the way, what that means for the concrete loops and loop order. I want to jump a little bit ahead because I think vectorization is straightforward, and also pre-computation of constant parts, so that we use here some tabulation, because this is one of the results now, basically showing, and I show that because that's based on a also on the roofline model. So you have here you are close to the model. Basically this is the measurement. I think we used liquid here. That was a Fritz result. Yes. And here we come relatively close. So it's not mentioned here how much percentage, but as you see, we are relatively close to the model.
What's the model in these curves?
So there is basically the middle one is the measurement here. This is the simple roofline model.
M lower is the roof. Sorry, I'm repeating for the people in Zoom who can't see the plot.
M upper and M lower. is here the roof line. And
You have a range.
yes, this is the upper and lower estimate, so to say.
Okay.
Yeah.
Okay, the graphs show that you are consistently in the range that your model predicts, the pessimistic and optimistic range of data volume.
So you can say, so we have here estimated the memory volume that has to be transferred to the, and the first two graphs, the first two lines in the legend, so the upper and lower bound, are very simplistic models. So for the upper bound, we assume that every time we need a value, so every time, so we element-wise, so we assume that every time we are on an element, we have to load 4 degrees of freedoms from memory. And the lower bound is extremely optimistic, saying that as we, or for an entire sweep over the grid, we just need to load every degree of freedom once.
That's the factor of 20 to 30 in difference,
Um,
at least in the left. It's 30.
Yeah.
Yes. And then we have two more bounds, which are the two middle ones, then are the measurements for what do we actually load. And the last two lines are some more sophisticated models where we determined some layer conditions and the cache sizes and then made a better prediction, which fits relatively well for the higher levels.
Yeah, this of course, yeah, I should have mentioned that LC is of course layer condition.
Very good. I like that.
Yeah. Yeah, I know that you like that. That's why we included it. Okay. Anyway, then basically what we also have in the publication is then of course that we have a kind of a roofline and the effect of the different optimizations. So you see here, for example, the vectorization and the loop invariance and so on, and this cubes loop. And if you turn on all of these different things, then you can achieve in principle here, okay, this is relative, does not say so much, 11 times speed up, but 62% of peak, I think it's quite okay for that kind of kernel. So yes, and this of course is now the benefit of the code generation, that you can do it also immediately for another PDE. So the same thing we did here for that one. And also we compared it to HyTeG, because those who may be attending the PerfLab seminar more often have also heard the talk about HyTeG. So HyTeG, for those who are familiar with code generation, HyTeG is also a kind of a framework that is able to generate, out of weak forms, efficient code. And of course, therefore, it was obvious to compare our approach here. And to say it before, it's not like HyTeG is now better or worse than our approach. We just had here a different kind of setting, because as you have shown, as I have shown in the beginning, we have one tetrahedra and then we have the refinement. So here for the HyTeG point, we have basically the tetrahedra and it's not refined. So therefore, this result shows you a little bit, okay, when is it beneficial to use our kind of grid to make this effort of refinement? Because of course, if you refine, you have additional communication. So you would expect, if you only refine once or twice, you're even maybe slower than just using HyTeG. And this is also shown here. So the first point is here, refinement level 3, and you see in this case we are kind of even slower than HyTeG. But then if we really have enough refinement, then our data structure pays off. We can make use of this regularity, so to say, for larger problems. And then also, of course, you see here the effect of our optimization. So without the optimizations, we are way slower than HyTeG. If we turn on all of our optimizations, we end up being a factor of 10 faster than this HyTeG variant here. So I think that was quite nice because it shows also there is no absolute better or worse. It always depends on your concrete setting, what you expect to do, what is your problem size, what grid do you have, and then there is an optimal, so to say, configuration for that. Yeah. Of course, I also have to show you a result on weak scaling on SuperMOOC and G. So that was a bigger result, so more than 10 to the power 12 unknowns. And of course, one thing, yes, it scales. So this is a good news. I think, correct me if I'm wrong, the reason why the coarse grid solver here kind of becomes more expensive is that you are using maybe a CG or so. Yeah,
Correct.
okay. So this is because of the algorithm. So that's maybe, yeah, so of course. So with the increasing number of points, you need then more effort on the coarse grid. Good. Okay. So there are 5 minutes left. So let's quickly come to waLBerla. So the good news, I have here only 2-3 slides about the code generation because I have now more or less said everything. waLBerla is our, yeah, I would call it working horse. Yeah, so there we have the most, yeah, diverse applications. We have not only fluid dynamics using lattice Boltzmann, we have also particles inside and free surface flows. So there's a large number of applications. And interesting for the code generation is, of course, the data structure. So this is an octree. And we also are able to do adaptive grids. So we can adaptively refine the octree, and we can also do load balancing, so dynamic load balancing. And of course, we support GPU and CPU. And our code generation pipeline looks like that. So we have basically 2 Python packages. One Python package called LBMPy, so that's the original publication here from Martin Bauer. Is basically a Python library that supports many of the current lattice Boltzmann variants, methods, and we are able to generate from a high-level representation kernels for these methods that are then in a second library called PyStencils translated into kernels. So that means the first library deals with the lattice Boltzmann method, and the output is then a SymPy-based expression, and this one is then translated into, for example, C++ or CUDA code. Of course, we also have some performance engineering results there, including, of course, models. Now we have basically a large number of things also implemented here. The big difference is that mainly we are using here the code generation for producing kernels. So that means you have then a kernel where you get a pointer to your data, and it, for example, does a LBM sweep. And then you can put this kernel into the library, and the library has to take care that you access the data in the correct way, right? Because you just get a pointer to the data, and it relies on the waLBerla framework to use it, yeah, in the right way. And of course, we have also extended that in the last years, especially also into the MPI and communication area, because since waLBerla is very often run on larger HPC clusters, the communication part is of course essential. We also support overlapping communication and computation, and therefore here we also include the kernels for the communication in the generation. So we can generate kernels for the communication part.
For overlapping, you rely on non-blocking MPI. You assume that MPI does it asynchronously.
We hope so. Yeah. Okay, so here I like that slide because it shows high-level code is readable, generated code is not readable, especially because it is small, and generic code is slow, and generated code is very fast. Yeah. So that's the take home. Yes, but of course it's very placative, but yeah. Yes, and also that we have applied to a number of different applications. I don't go into detail here because we are coming towards the end. The last real slide I want to show is the recent features for code generation, because of course we are working on it also right now, also besides HyTeG, of course, in waLBerla. And here I have to mention, for example, that we are now able to also support non-uniform communications on GPUs. Why do I mention that here? Because, of course, it's kind of a library, this code generator. So if you want to add support for this kind of special kernels for non-uniform communication on a GPU, you have to implement it in the code generator. So that's, of course, the effort it takes. But once it is implemented, we will then be able to run it, for example, on different GPUs, or maybe also using a SQL backend and run it on other platforms. And we did some work on reductions and optimized that. And also, maybe I want to mention that we lately had, by Raphael, particle simulation also implemented as a code generation approach that allows us now also to run the particle simulations fully on GPU, for example. Yes, so that's more or less what I wanted to say. A lot of things are ongoing. I guess most of you are not astonished about that. So we are now also involved in research software engineering. Performance portable code is still a big topic. Mixed precision is currently interesting, and of course also surrogate models, the AI, and the number of multiphysics applications we are supporting and trying to implement in waLBerla. Okay, so thank you very much, and I'm done.
All right. So are there any questions or points for discussion here in the room? In the Zoom, please raise your hand or put your question in the chat. There's one question in the chat I can read right away. Do all code generation create a C++ or so codes that will be compiled to machine codes by compiler, or can it go lower level than that?
Of course, it can go lower level if you use LLVM, for example, so the ML or IR. So we typically use a higher level code, but it's not restricted to that. So you can, of course, also have more low-level code generated. So there was a question?
Yeah, I'm still not sure if I really got it, how it works. I mean, you emphasized you want to be able to generate optimized code for different machines, for different platforms. So now, depending on the machine, you have many possibilities on how the code can be made faster. Do you now, in your code generator, have to kind of implement for each type of machine you have in mind your kind of own translator? Or do you have kind of a set of possibilities and you have then to say what you think is the right combination of possibilities that will be the fastest on that machine? Or how can I think about that?
So in fact, that's of course the tedious and the long time-taking part. So you have to implement all backends. So like HIP, SYCL, C++, Fortran, whatever. So everything you want to support, of course, you have to kind of provide MPI support if it's not done by the library. Yes, you have to implement all variants. But usually this is kind of modular because then you can, for example, combine different transforms. And this is kind of a large search space. So you need some, either if it's a smaller problem, some auto-tuning. If it's a larger problem, you may ask Dinesh to start his genetic programming approach. But yes, it's of course it's not so easy to optimize to find the optimal combination of parameters if you have a large search space. Yeah. So usually, of course, there is also a lot of smartness going in. For example, for HyTeG, they think about the mathematical features and then select those things where they think, okay, this is hopefully the best. Yeah.
Okay, so that means, let's say you can have a machine where the nodes are faster, but the communication is slower, and another one where you have faster communication and then slower nodes. So now you can decide, do I batch messages that I have less communication or reorder the loops and so on. So did I get it right? So the code generator can now do different variants between the loads, but then for optimizing it for now specific machine, you then have to run an optimization procedure on that.
Yeah. Yes, either you do it manually or you have an optimizer running and basically generating then, I don't know, 100,000 variants, running them. So we also had, of course, work in that direction, but in general, that's quite difficult to find a very good optimizer. It depends. No? No.
Maybe one more question from me. Now, there's a lot of software you've developed, several people over years. How maintainable is the whole software framework? I mean, language standards change, compilers change, things get deprecated, software ages. Okay. So if I want to use this in 10 years, yes.
Yeah, that's a big problem. And this is what we call now currently the research software engineering. Because we have, as you say, we have so many variants, yeah, and it's not only that it's difficult to run a code that was written 10 years ago, but also if you add a new feature, it's not clear if the whole program is not slowed down or something like this. And the current approach we are following is we try to have continuous benchmarking, continuous integration. As you know, we have this pipeline set up here at the test cluster, and but that will be a research topic also in the next years. Yes, so I agree. This is a big issue.